Everything you see around you was once packed into a space smaller than an atom. The universe's architecture began from a single, hot, dense point, and its evolution is the most epic story ever told. By the end of this journey, you will understand how the entire cosmic web, from galaxies to planets, was built step by step. We will uncover how a featureless primordial soup transformed into a structured cosmos, and discover the mysterious forces like dark energy that now control its fate. How did random quantum jitters create the blueprint for everything? What does the accelerating expansion of space mean for our ultimate future? What part of this cosmic story is most surprising to you? The very fabric of reality was not yet woven. We step back into the Planck epoch, a duration so brief it defies human comprehension, the first sliver of existence where our current understanding of physics simply stops working. This was not merely a hot, dense state. It was a realm of pure potential, a seething quantum foam. In this primordial chaos, the four fundamental forces that govern our universe, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into one singular, ultimate superforce. There was no separation, no distinct interactions, just a unified power ruling over a domain where space and time themselves churned and fluctuated. The idea of a sequence, of a moment before followed by a moment after, loses all meaning here. It was a state of such extreme energy and density that the concepts of here and there, then and now, dissolve into an indistinct haze. This is the ultimate frontier for cosmologists, a chapter of cosmic history written in a language we are still struggling to decipher. Our most advanced theories can only point toward its existence, a mysterious foundation upon which everything else would be built. From this formless, chaotic canvas, the first brushstrokes of structure were about to be applied, initiating a transformation more dramatic than any we can conceive. Out of that formless quantum foam, an event of unimaginable ferocity was unleashed. In a span of time so brief it makes a blink seem eternal, the fabric of space itself erupted in a hyper-fast expansion. Think of a single microscopic dot, and in an instant smaller than any you can conceive, it swelled to a size larger than our entire observable universe. This was the inflationary epoch, the cosmos's own breathtaking growth spurt. This wasn't just fast expansion, it was exponential, with space stretching faster than light itself could travel across it. This incredible violence solved profound mysteries. It explains why the universe, when we look in every direction, appears so remarkably uniform. Before inflation, different regions could have been wildly different, but this rapid stretching smoothed everything out, ironing the cosmos into a state of homogeneity. Yet, within that smoothing process, something crucial was happening. The microscopic quantum jitters from the Planck epoch, those tiny fluctuations in energy, were suddenly stretched to monumental proportions. Imagine tiny ripples on a pond being instantly enlarged into continent-spanning waves. These ripples in density became the cosmic blueprint, the gravitational seeds for everything to come. Every galaxy, every cluster of galaxies, exists today because of those infinitesimal imperfections magnified during inflation. We can still see the echoes of this event imprinted on the oldest light in the universe, the cosmic microwave background, like a fossilized photograph of the universe's first moment of structure. With this foundational canvas now prepared, the furious expansion ceased, and the universe was ready to build something tangible from the void. The furious stretching of inflation ceased, but its energy had to go somewhere. That released power flooded the nascent cosmos, reheating it into a seething, blindingly bright primordial soup. For hundreds of thousands of years, the universe was an opaque plasma, a dense fog where particles were born and annihilated in a constant, chaotic dance. Quarks, electrons, and photons were trapped in a relentless embrace, colliding and interacting so frequently that light could not travel freely. Within this inferno, a profound and critical imbalance was established. For every 1 billion particles of antimatter, 1 billion and 1 particles of matter came into existence. This tiny 1 in a billion asymmetry, a process called baryogenesis, is the only reason anything substantial exists today. Had matter and antimatter been perfectly equal, they would have completely annihilated each other, leaving behind a universe of pure, featureless radiation. We are here because of that one, fragile, extra piece of matter in a billion. As expansion continued, the cosmos cooled just enough for a new chapter in structure building to begin. The quarks swirling in that hot soup finally lost their independence and combined, locking together in groups of 3 to form the first protons and neutrons. These are the bedrock building blocks of atomic nuclei, the very anchors of all visible matter. This was a period of constant transformation, where the fundamental ingredients for everything we know were forged in the universe's incredible heat. The conditions of this specific era, its density and temperature, acted like a cosmic recipe, determining the initial abundance of the simplest elements. Almost all the hydrogen and helium in the universe today was cooked in those first few minutes, a primordial fuel that would later ignite the first stars. From a chaotic, opaque inferno, the first stable structures of matter were now emerging. The universe was on the cusp of a monumental clearing, a transition that would finally allow light to fly free across the cosmos. That chaotic fog of light and matter finally began to clear. For nearly 400,000 years, the universe expanded and cooled, until it reached a critical temperature threshold. This moment, called recombination, marked a fundamental shift. Electrons, which had been racing freely through the hot plasma, were finally captured and bound by the atomic nuclei that had been waiting in the cosmic soup. They settled into orbit, forming the very first stable, neutral atoms, almost all of them simple hydrogen and helium. With this single event, the universe underwent a stunning transformation. It became transparent. Before this, the cosmos was an impenetrable glow, a dense fog where photons of light could not travel any meaningful distance without colliding with a free electron. But once those electrons were locked safely inside atoms, the roads were cleared. Light was suddenly set free. That first flash of liberated light, a brilliant afterglow from the universe's hot youth, still washes over us today. We detect it as the cosmic microwave background, a faint whisper of radiation that permeates all of space. This is not just ancient light, it is a cosmic fossil, a baby picture of the universe frozen in time. And etched into this fossil are incredibly subtle patterns, tiny variations in temperature from one patch of sky to another. These minute fluctuations are the gravitational seeds from the inflationary epoch, now imprinted onto the light itself. They are the blueprints for everything, the subtle overdensities that would determine where the first galaxies would be born. With the fog lifted, the universe entered its dark ages. The brilliant glow of recombination faded, and no new light sources yet existed. For millions of years, the cosmos was a vast, dark, and expanding sea of neutral hydrogen gas, silent and still. It was a cosmic intermission, a period of quiet patience. But within that profound darkness, the blueprints were already drawn. Gravity, the most patient force of all, was beginning its slow, relentless work, pulling ever so gently on those slightly denser patches of gas. The universe was holding its breath, poised for a spectacular awakening, waiting for the first stars to ignite and shatter the silence forever. For millions of years, a profound silence fell across the cosmos. This was the Dark Ages, a deep and expansive lull where the universe was cloaked in a pervasive, dark fog of neutral hydrogen gas. The brilliant flash of liberation had passed, and the fading afterglow of the cosmic microwave background slowly reddened, shifting into invisible infrared light. Yet, within this apparent stillness, the most patient force in the universe was at work. Gravity, acting on the faint blueprints left over from inflation, began its slow, relentless pull. Those subtle ripples in density, the ones we see imprinted on the ancient light, started to gather more and more of the primordial gas. Vast, dark clouds of hydrogen and helium began to collapse under their own weight, a process so gradual it would be imperceptible over a human lifetime, but unstoppable across cosmic timescales. This era was not a void of inactivity, but a necessary incubation, a period of cosmic patience where the simplest ingredients were quietly assembling into the first complex structures. Deep within these collapsing clouds, the potential for a spectacular revolution was building, compressing and heating the gas until the conditions for nuclear fusion were nearly met. The darkness was a cradle, a necessary quiet before a storm of light would forever change the universe. This great silence was about to be broken by the ignition of the very first stars, an event that would trigger a dramatic transformation known as reionization. The deep cosmic silence was finally shattered. From within those vast, dark clouds of hydrogen and helium, the very first stars ignited. These were not like the stars we see today. They were colossal behemoths, the universe's first pioneers known as population 3 stars. Composed of nothing but the pristine, primordial elements of hydrogen and helium, they burned with a ferocious, ultraviolet intensity, living fast and dying young in spectacular supernova explosions. Their brilliant birth marked the beginning of a new cosmic revolution, an era known as Reionization. The intense radiation pouring from these first stars and the earliest quasars began to flood the surrounding darkness. This powerful light acted like a cosmic blowtorch, striking the neutral hydrogen atoms that filled the universe and violently stripping away their electrons. The vast, dark fog of the intergalactic medium was being systematically dismantled, transformed once again into a transparent, ionized plasma. This time, however, the universe did not become an opaque fog. Its expansion had lowered the overall density of matter, allowing light to travel freely even through this newly ionized sea. Reionization was not a single, instantaneous flash that lit up the entire cosmos. Instead, it was a slow, patchy process that unfolded over hundreds of millions of years. Imagine countless isolated islands of brilliant light, each one a bubble of ionized gas surrounding an early star or quasar. Over immense timescales, these individual bubbles grew larger and larger, eventually merging and overlapping until the entire cosmic volume was once again filled with transparent, ionized gas. This monumental transition fundamentally altered the fabric of the universe. It cleared the final obstacles for light, allowing it to travel across vast cosmic distances unimpeded. It also pumped enormous energy back into the intergalactic medium, heating it and changing its fundamental properties. This heated environment became the new stage, the prepared canvas upon which the next great act of cosmic construction would unfold. The Dark Ages were over for good. The universe was now permanently lit, its shadows pushed back, ready for the magnificent era of galaxy assembly to begin in earnest. These first protogalaxies were the universe's earliest cities, emerging from the dark. They were not the majestic spirals we know today, but rather small, irregular collections of stars and gas, perhaps only 1/100th the mass of our own Milky Way. Their formation was a violent and chaotic process, driven entirely by the relentless pull of gravity. Countless of these small building blocks swarmed through the early cosmos, frequently colliding and merging in a dramatic dance of creation and destruction. With each titanic merger, streams of gas were compressed, triggering ferocious waves of new star formation and drawing the structures into larger, more massive galaxies. This was a period of intense construction, where the cosmic landscape was being forged through a series of colossal impacts. Inside these stellar nurseries, the cycle of life and death for stars began to fundamentally change the universe's chemistry. The first generation of massive stars lived short, brilliant lives and died in supernova explosions, scattering their enriched guts across the cosmos. These stellar explosions seeded the surrounding gas clouds with newly forged elements, the first carbon, oxygen, and iron. This process, known as chemical enrichment, was a pivotal turning point. Before this, the universe contained only the two simplest elements, hydrogen and helium. Now, with these heavier metals available, the universe could build so much more. The formation of dust grains and complex molecules became possible. Most importantly, this enrichment paved the way for the formation of rocky planets like Earth and the eventual chemistry of life itself. We are literally made of stardust, the recycled remnants of those early giant stars that lived and died billions of years ago. These first galaxies were more than just collections of stars. They were the cosmic engines that transformed a simple, pristine universe into a complex and chemically rich one. They laid the foundational bricks for the vast cosmic metropolis we observe today, a sprawling web of galaxies, clusters, and filaments. The universe was no longer just a collection of blueprints. It was a dynamic, evolving construction site, building its grand architecture one merger at a time. The grand tapestry of galaxies we observe today would simply not exist without an invisible cosmic framework. While stars and planets capture our attention, they represent only a tiny fraction of the universe's total content, a mere 5%. The true architect of cosmic structure is a mysterious and invisible substance known as dark matter. This enigmatic component makes up roughly 27% of the universe, and though it neither emits nor absorbs light, its gravitational influence is absolutely dominant. It acts as the invisible scaffolding for the entire cosmos. After the initial blueprints were set by inflation, dark matter began to clump together first, forming a vast, web-like network of gravitational wells. The ordinary matter, the gas and dust we can see, simply followed this hidden template, flowing into these pre-existing pits and valleys to eventually form galaxies and clusters. Without the relentless gravitational pull of dark matter, the initial density fluctuations from the Big Bang would have grown far too slowly. The universe would be a much more diffuse and empty place, with no galaxies having had enough time to form within its current age of nearly 14 billion years. We cannot see dark matter, so how do we know it is there? The evidence is compelling and comes from multiple independent observations. The rotation speeds of stars within spiral galaxies are too fast to be explained by the gravitational pull of visible matter alone, suggesting a massive, unseen halo of dark matter must be holding these galaxies together. We see it in the way massive galaxy clusters bend light from distant objects behind them, an effect called gravitational lensing, which reveals the presence of far more mass than we can account for with stars and gas. And we see its crucial signature imprinted in the precise patterns of the cosmic microwave background, where its gravitational influence affected how the primordial plasma sloshed back and forth. Dark matter is the silent, unseen partner in the cosmic construction project, the hidden framework upon which every galaxy, every star, and every planet is built. Understanding this invisible component is the key to finally deciphering the universe's deepest architectural plans. We have been building this story from the quantum scale, but the true grandeur only appears when we pull back to the widest possible view. The universe is not a random scattering of galaxies. It is structured on the largest scales into a breathtaking cosmic web. This is the ultimate architecture of reality, a vast, interconnected network of galaxies, clusters, and superclusters, all strung along immense, invisible filaments of dark matter and separated by unimaginably enormous voids. Picture the structure of a sponge, or perhaps the neural connections of a colossal brain, and you begin to grasp its intricate form. This is not a static sculpture. It is a dynamic, flowing river system on a cosmic scale. For billions of years, gravity has been the master sculptor. guiding ordinary matter along these dark matter highways, pulling it into dense nodes where thousands of galaxies swarm together in massive clusters. These clusters are the great cities of the cosmos, the intersections of the web. But what of the spaces in between? The voids are not empty, but they are regions of exceptionally low density, making up most of the actual volume of the universe. They are the cosmic countryside, vast and quiet, stretching for hundreds of millions of light years. How do we know this web exists? We have mapped it. Enormous astronomical surveys, which have painstakingly catalogued the positions of millions of galaxies, reveal this precise, frothy pattern across the sky. And the most stunning part is that this grand design, this sprawling metropolis of galaxies, perfectly matches the subtle blueprints we see imprinted in the cosmic microwave background. Those tiny temperature fluctuations from the universe's infancy are the direct ancestors of the cosmic web we see today. Every filament you are part of, every cluster, every vast empty void, is the ultimate expression of gravity's patient work, a universe sculpting itself into an interconnected whole over billions of years. This web connects everything, from the smallest dwarf galaxy to the largest supercluster, in a single, flowing cosmic structure. At the dense intersections of the cosmic web, the universe builds its great cities. These are the galaxy clusters, the most massive structures held together by gravity. A single cluster is a metropolis of staggering proportions, hosting not hundreds, but often thousands of individual galaxies, all swarming around a common center. But the galaxies themselves are only the visible citizens of this cosmic capital. They are immersed in a vast, seething ocean of superheated gas, so hot that it glows not with visible light, but with intense X-rays. This intergalactic plasma is a relic of the primordial material that flowed into this deep gravitational well, and it contains more ordinary mass than all the stars in all the cluster's galaxies combined. And binding it all together is the true sovereign of the cluster, an immense, invisible halo of dark matter whose gravitational grip is the only force powerful enough to prevent such a dynamic system from flying apart. These clusters are not quiet, stable places. They are constantly evolving, growing over billions of years by drawing in new galaxies from the web-like filaments that connect them, like a sprawling city annexing its suburbs. Sometimes, these cosmic metropolises engage in the most violent construction process of all, merging with other clusters in collisions that release more energy than any event since the Big Bang itself. These events are natural laboratories, allowing us to see how different components of the universe behave. During a merger, the dark matter halos, the X-ray gas, and the galaxies themselves all interact in revealing ways, providing some of the strongest evidence for the existence of dark matter. On an even grander scale, these clusters themselves group together into superclusters, the continents of the cosmic web. A supercluster is a vast collection of clusters and groups, but here we reach a critical limit of gravity's influence. Unlike a bound galaxy cluster, a supercluster is not held together by its own gravity. The distances are simply too vast. Instead, these immense structures are temporary arrangements, their member clusters destined to be slowly pulled apart over cosmic time by the relentless expansion of the universe itself. By mapping and studying these great cities and continents of space, astronomers can perform a remarkable feat. They can weigh the entire universe. They can measure the total amount of dark matter and dark energy by observing how these largest structures form and evolve. They represent the pinnacle of cosmic architecture, the final destination in the flow of matter that began with those tiny quantum ripples. From a formless primordial soup to a structured web of brilliant cities, the universe's construction project reveals a scale of organization that is both humbling and breathtaking. Those primordial blobs of stars and gas were cosmic infants, chaotic and full of raw potential. They did not simply drift through the void, they grew up. and their journey from turbulent youth to majestic maturity is written in their very shapes. A galaxy's form is a living record of its past, a chronicle of collisions, bursts of creation, and internal revolutions. In their early years, galaxies were often messy and irregular, brimming with cold, primordial gas. This abundant fuel led to ferocious waves of star formation, lighting them up with brilliant, short-lived blue stars. But this frantic construction could not last. The very processes that built them also began to shape and regulate their growth. When the most massive of these young stars died, they did not go quietly. Their supernova explosions were titanic, releasing vast amounts of energy that heated the surrounding gas or even blew it clear out of the galaxy altogether. This self-regulation, known as feedback, put a brake on runaway star formation. In the most massive galaxies, an even more powerful engine took control, the supermassive black hole at its core. As matter spiraled into this gravitational abyss, it formed an active galactic nucleus, a quasar whose intense radiation and powerful jets could heat galactic gas on a tremendous scale, effectively shutting down star formation for eons. These internal processes act as a galaxy's own metabolism, determining its pace of life and eventual fate. The most dramatic transformations, however, came from the outside. Galaxy mergers were the great turning points in this evolutionary story. When two gas-rich galaxies collided, it was not a destructive crash, but a creative one. Their mutual gravity would disrupt their serene structures, funneling vast reservoirs of gas toward their centers and triggering a firestorm of new star formation, a starburst that could create millions of stars at once. The final outcome of this cosmic dance depended on the partners involved. The majestic spiral galaxies, like our own Milky Way, are often the result of a more orderly growth, steadily absorbing smaller satellites and maintaining a rotating disk of gas and stars. The giant elliptical galaxies, by contrast, are the cosmic retirement homes for stars. They are often the product of major mergers between two large spirals, a violent event that randomizes stellar orbits, consumes the remaining gas, and leaves behind a smooth, featureless sphere of aging red stars. This is why we see such a stunning diversity in the galactic population. A galaxy's color, its shape, its stellar population, they all tell a unique story. A red and dead elliptical recounts a history of a dramatic, final merger that exhausted its fuel. A bright blue spiral speaks of a quieter life, with a steady supply of gas and ongoing, peaceful star formation. Their evolution is far from over. Even now, galaxies continue to change, influenced by their address within the cosmic web. A galaxy living in a dense cluster faces a harsher environment, with its gas often stripped away by interactions with the cluster itself, while a galaxy in an isolated filament may enjoy a more serene existence. This grand morphological transformation, from simple blobs to complex spirals and ellipticals, is a testament to a dynamic and evolving universe, one where even the largest structures are in a constant, beautiful state of becoming. These gravitational monsters are far more than cosmic vacuum cleaners. Lurking in the heart of nearly every large galaxy is a supermassive black hole, an entity so dense that its gravity can trap light itself. Their masses are almost incomprehensible, ranging from millions to billions of times the mass of our own Sun. Yet their true significance lies not in their destructive power, but in their surprising role as cosmic regulators. When such a black hole actively feeds, pulling in vast quantities of surrounding gas and dust, it does not do so quietly. The infalling material swirls into a superheated accretion disk, and this process transforms the black hole into an engine of unimaginable power, a quasar or active galactic nucleus. The energy released can outshine the entire galaxy that hosts it. This is where the magic of feedback occurs. The intense radiation and powerful jets of particles erupting from the poles of this engine blast outwards, heating the surrounding reservoir of galactic gas. When gas is heated, it becomes too energetic to collapse and form new stars. In this way, the black hole acts as a cosmic thermostat, turning down the star formation rate in its own galaxy, and ultimately putting a ceiling on the galaxy's growth. This creates a profound and delicate balance. The same process that feeds the black hole and gives it power is also the process that eventually shuts down its own fuel supply. This intricate dance suggests a deep, symbiotic relationship. Astronomers have found a tight correlation between the mass of a galaxy's central bulge of stars and the mass of its central black hole. It is as if the galaxy and its dark heart grew up together, their fates inextricably linked through a cycle of feeding and feedback. These black holes are not mere passengers, they are integral components of the galactic ecosystem. Their growth histories are woven directly into the story of their host galaxies, ensuring a balance between the chaos of unfettered star formation and the orderly structure of a mature galaxy. They are the ultimate cosmic regulators, governing from the shadows and shaping the very architecture of the universe on a grand scale. For billions of years, the universe's expansion was slowing down. Every galaxy, every particle of dark matter, every wisp of gas exerted a mutual gravitational pull, a cosmic tug of war against the initial momentum of the Big Bang. This was the Great Deceleration, a period where gravity was steadily applying the brakes on the cosmos. But this narrative of a gradual cosmic slowdown was completely upended by a discovery that stunned astronomers at the close of the 20th century. Two independent teams were measuring the distances to extremely far-off supernovae, using them as cosmic mile markers to gauge how the expansion rate had changed over billions of years. They expected to confirm the slowdown. Instead, they found the opposite. The most distant stellar explosions were fainter than expected, indicating they were farther away than anyone had predicted. The only possible explanation was that the expansion of the universe was not slowing down at all, it was speeding up. This was not a subtle effect, it was a fundamental shift in the behavior of the cosmos itself. Something was overcoming gravity's grip and pushing the galaxies apart with ever-increasing force. That something was given a name, dark energy. This mysterious repulsive force now makes up about 68% of the entire energy content of the universe, making it the dominant component governing cosmic dynamics. The transition point, when dark energy's push finally overwhelmed gravity's pull, occurred roughly 5 billion years ago. Before that pivotal moment, the architecture of the universe was shaped primarily by the relentless pull of gravity, building galaxies and weaving the cosmic web. Since that moment, a new and dominant force has taken the helm, one that is stretching the very fabric of space itself. This acceleration has profound implications for the future of cosmic structure. While gravity continues to build local structures like our own Milky Way galaxy, on the very largest scales, the accelerating expansion is beginning to pull the universe apart. The cosmic web, that magnificent sponge-like structure, will eventually be stretched and diluted. Distant galaxy clusters, now connected by filaments, will be isolated as the space between them expands faster than light can traverse it. The nature of dark energy remains one of the most profound puzzles in all of science. Is it a constant energy inherent to the vacuum of space itself? Or is it a dynamic field that could change over time? The answer will ultimately determine the final architectural plan for our universe, a fate written in a language we are only just beginning to understand. The faint imprint of those primordial sound waves is still visible today. Etched into the very distribution of galaxies across the cosmos is a ghostly signature, a phenomenon known as Baryonic acoustic oscillations. To understand this, we must return to that hot, dense plasma before the universe became transparent. In that searing soup, ordinary matter, or baryons, was tightly coupled with light. This created a unique effect. Regions of slightly higher density had stronger gravity, pulling in more material, But the intense radiation pressure from the trapped photons created a counteracting force, pushing the material back out. This push and pull set the entire plasma ringing with powerful sound waves that raced outward at over half the speed of light. For nearly 400,000 years, these spherical pressure waves expanded through the early universe, carrying shells of compressed matter with them like ripples from a stone thrown into a pond. Then, in an instant, the music stopped. When recombination occurred and atoms formed, the universe suddenly became transparent. The photons, which had been providing the pressure, flew away and the waves froze in place, mid-ripple. These frozen shells of matter became the preferred locations for galaxies to form billions of years later. This left a subtle but measurable pattern in the cosmos. Galaxies are ever so slightly more likely to be found separated by a specific distance, the radius of that ancient sound wave at the moment it was frozen. Today, that preferred scale measures about 500 million light-years across. For astronomers, this frozen wave is a gift, a cosmic standard ruler. By surveying millions of galaxies and measuring the apparent size of this ruler at different distances, and thus different eras in cosmic history, we can track with incredible precision how the expansion of the universe has stretched space over billions of years. It is a direct probe of dark energy's influence, allowing us to see how its repulsive force has changed the rate of expansion. This acoustic fossil, a direct echo from the universe's first moments, provides one of our clearest three-dimensional maps of the cosmos's grand architecture, revealing the hidden forces that continue to shape our reality. Einstein's revolutionary insight was that space is not a static stage, but a dynamic fabric that can be warped and curved by mass. This curvature guides the path of everything moving through the cosmos, even something as seemingly straight as a beam of light. When light from a distant galaxy travels toward us and passes near a massive object like a galaxy cluster, its path is bent, just as a glass lens bends light. This effect, gravitational lensing, transforms the universe into a colossal observatory, allowing us to see the invisible. We can now map the dark matter that dominates the cosmos by watching how it twists the light from background galaxies. In its most dramatic form, known as strong lensing, the distortion is breathtaking. A single distant galaxy can be smeared into a luminous arc, or even split into multiple, perfect images encircling the foreground cluster like a cosmic mirage. These Einstein rings and multiple images are not just beautiful illusions, they are powerful tools. They act as natural telescopes, magnifying the light of incredibly faint, ancient galaxies that would otherwise be far beyond our view, giving us a direct window into the early universe. But the most common form of this phenomenon is far more subtle. Weak gravitational lensing causes a slight, systematic stretching in the shapes of millions of background galaxies. By surveying vast patches of the sky and meticulously measuring these tiny distortions, astronomers can create a three-dimensional map of the dark matter web, tracing the invisible filaments and halos that constitute the universe's true backbone. This technique allows us to literally weigh gigantic galaxy clusters, simply by observing how severely they bend the light from objects behind them. The results consistently show that there is far more mass present than the visible stars and gas can account for, offering some of the most direct and compelling evidence for the existence of dark matter. By decoding these cosmic mirages, we are not only testing the fundamental laws of gravity on the largest scales, but we are also peering directly into the hidden architecture of reality, using bent light to illuminate the dark. The grand cosmic web, with its brilliant cities of galaxies and flowing filaments, will not endure forever. The same dark energy that now dominates the cosmos is scripting a far lonelier future, one where the very architecture we have traced will slowly fade from view. In tens of billions of years, the relentless acceleration of space will pull apart the universe's largest structures, galaxies outside our own local gravitationally bound group, will have their light stretched to such long, invisible wavelengths that they will effectively vanish from our observable sky, receding beyond any possible contact. The universe will become a collection of isolated island universes, drifting apart in an ever-expanding sea of darkness. Within these remaining galaxies, the era of star formation will also draw to a close. The interstellar gas, the raw material for new suns, will either be locked away in aging stars and stellar remnants, or become so diffuse from the expanding volume that it can no longer collapse to ignite new nuclear fires. The last generation of stars will flicker out, leaving behind a cosmic population of fading embers, white dwarfs, neutron stars, and the silent, ever-watchful black holes. This, however, is not the final act. On timescales so vast they defy comprehension, even these remnants face their own dissolution. Current theories suggest that the very protons that form the bedrock of all atomic matter may not be truly stable, but could decay over countless eons, causing every remaining structure to gradually evaporate into a sea of fundamental particles and energy. And in perhaps the most profound transformation of all, the black holes themselves, those seemingly eternal gravitational anchors, are predicted to slowly leak their mass away through a process known as Hawking radiation, eventually vanishing in a final, faint puff of particles. The end point of this unimaginably long journey is a state known as the heat death, a universe that is uniformly cold, utterly dark, and essentially empty, having reached a state of maximum entropy where no energy can be harnessed to do work, and no new structures can ever form again. This long-term forecast presents a cosmos where the story of structure is ultimately a transient, though magnificent, chapter. All the brilliant construction, from the first quantum seeds to the great galactic cities, represents a fleeting moment of intricate order in an otherwise featureless and expanding void. While this vision is based on our current understanding of physical laws, it invites a profound reflection on the nature of our universe. It suggests that the cosmos is not in a state of permanent structure, but is instead engaged in a constant, dynamic dance between the forces of construction and dissolution, with dark energy holding the final note. The entire epic of cosmic architecture, from the first spark to the last fading echo, is a story written in sand, destined to be washed away by the timeless tides of space itself. The universe we have mapped so meticulously may be just a single room in an infinite cosmic mansion. This is the Multiverse Hypothesis, a staggering idea born from the mathematics of cosmic inflation. The theory of eternal inflation suggests that the rapid stretching of space that shaped our early cosmos never truly stopped everywhere. Instead, it may be a perpetual engine, with new pocket universes continuously bubbling into existence, each one a separate domain with its own unique physics. Within this infinite ensemble, the fundamental laws we take for granted become local ordinances. The strength of gravity, the mass of an electron, the very number of spatial dimensions could all be different in these other realms. In some bubbles, gravity might be so strong that stars form and burn out in an instant. In others, the forces might be too weak to ever bind atoms together at all. Our universe, with its specific blend of particles, forces, and its puzzling amount of dark energy, might not be a finely tuned masterpiece, but simply a lucky draw from a cosmic lottery. This concept offers a potential answer to one of the deepest mysteries in science, the Anthropic Principle. Why does our universe appear so perfectly calibrated for complexity and life? If an infinite number of universes exist with all possible laws, then it is no surprise we find ourselves in one of the rare, hospitable ones that allows for galaxies, stars, planets, and observers. There is no need for a designer, just the sheer statistics of infinity. This idea fundamentally redefines what we mean by the universe. The entire observable cosmos, with its billions of galaxies stretching back to the cosmic microwave background, becomes merely our local neighborhood, our bubble. The grand architecture we have been exploring is not the totality of existence, but simply the physics of our particular domain. While this remains a speculative frontier, untestable with current technology, it pushes cosmology into profound philosophical territory. It forces us to confront the nature of reality itself and question whether our most fundamental laws are truly universal or merely provincial. Our ability to observe this cosmic story is perhaps its most remarkable feature. Why does the universe possess such a specific, delicate recipe for complexity? The fundamental constants of nature seem perfectly calibrated for building a structured cosmos. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself long ago. If it were marginally weaker, matter would never have clumped together, and galaxies would never have formed. The same is true for the cosmological constant, the value governing the strength of dark energy. Had it been a little larger, the accelerating expansion would have torn apart the seeds of galaxies before they could even grow. Had it been smaller, the universe might have collapsed before life could arise. This apparent fine-tuning is one of the deepest puzzles in science. The Anthropic Principle offers a unique perspective on this mystery. It suggests that the universe we observe must be compatible with the existence of observers. In other words, we should not be surprised to find ourselves in a universe that allows for our own existence. This is not a traditional causal explanation, but a profound selection effect. Our very presence as conscious beings filters the kind of cosmos we are capable of seeing. Within the vast landscape of a possible multiverse, we do not inhabit a typical universe, we inhabit a viable one. We find ourselves in one of the rare bubbles where the cosmic lottery produced the right numbers for stars, planets, and ultimately, life. This principle weaves our own consciousness directly into the fabric of cosmology. The fact that we are here to map the cosmic web and ponder dark energy is a direct, logical consequence of an architecture that allows for such complexity. It connects the grandest scales of galaxy clusters to the most intimate scale of a living, questioning mind, adding a final, self-aware chapter to the epic of cosmic construction. This sprawling cosmic web of galaxies and dark matter raises a question that echoes across the void. Are we its only conscious inhabitants? As we map this grand design, the search for meaning leads us to look for neighbors, to scan the heavens for signs of technology or technosignatures. These are not messages in a bottle, but the indirect traces of an advanced civilization, perhaps the energy signature of a vast engineering project, the chemical fingerprint of industrial pollution in a distant exoplanet's atmosphere, or the deliberate beam of a focused communication laser. If life and intelligence are natural outcomes of cosmic evolution, then this magnificent architectural structure, with its hundreds of billions of galaxies each containing billions of stars, should be absolutely teeming with activity. The silence we have encountered so far, the profound quiet we hear when we listen, presents a puzzle known as the Great Filter. It suggests that there may be a critical, difficult step in the progression from non-living matter to a spacefaring civilization that most potential life forms never overcome. This barrier could be the inherent fragility of complex biological life, the self-destructive nature of developing advanced technology, or simply the staggering improbability of all the right conditions aligning for long enough. Our search for these cosmic signatures is ultimately a search for our own place within this immense metropolis. Finding even a single, faint signal would revolutionize our understanding of existence, telling us that the universe's laws not only allow for life, but also for the enduring emergence of conscious, technological minds. It would mean we are not a solitary accident, but part of a larger cosmic community. Conversely, if we continue to find only silence, it places a profound responsibility upon us. It would suggest that in this entire vast architectural plan, we may be the only ones currently capable of understanding its beauty, of tracing its history, and of acting as stewards for the fragile spark of consciousness. The answer, whether we are a common story or a singular narrative, defines our ultimate significance in the cosmos. Our most precise map of the universe may contain a fundamental crack. For decades, the lambda-CDM model has stood as cosmology's robust standard, a framework that elegantly explains the cosmic microwave background, the abundance of light elements, and the large-scale structure of the cosmic web. This model is the detailed blueprint we have been following throughout our entire journey. Yet, a persistent and growing discrepancy now challenges this elegant consensus, a puzzle known as the Hubble Tension. It revolves around a single critical number, the Hubble constant, which measures the current rate of the universe's expansion. The problem is this: when we measure this expansion rate by looking at the very early universe, using the pristine snapshot of the cosmic microwave background, we get one value. But when we measure it using the late universe, by observing the distances and redshifts of nearby supernova and other stellar markers, we get a consistently different, faster value. These are not rough estimates. Both methods have been refined to extraordinary precision, and yet they stubbornly disagree. It is as if you used two perfectly accurate rulers to measure the same object and got two different results every single time. This is not a small statistical fluke. It is a significant tension that suggests something in our standard model might be incomplete or subtly wrong. What could be causing this rift in our cosmic measurements? The possibilities are as exciting as they are profound. Perhaps there is an unknown form of dark radiation, an exotic particle that flooded the early cosmos and altered its expansion history. Maybe dark energy is not a constant vacuum energy as we have assumed, but a dynamic force that has evolved over billions of years, changing its strength and influence. Or the solution could lie in a deeper understanding of the dark matter particle itself, endowing it with properties we have not yet considered. Of course, there is always the chance of an unaccounted-for systematic error in our measurements, a subtle bias that has crept into our observations. Resolving this puzzle is a primary driving force behind a new generation of powerful telescopes, from the James Webb Space Telescope to massive ground-based observatories. They are scrutinizing the cosmic distance ladder, searching for any overlooked rungs, and peering back to the epoch of the first galaxies to cross-check our cosmic timeline. The Hubble Tension is a powerful reminder that our understanding of the universe's grand architecture is not a finished book, but a living document, constantly being revised and updated. This discrepancy is not a failure of science, but a thrilling opportunity, a potential window into new physics that could ultimately lead to a revolutionary rewrite of our standard model of cosmology. The Hubble Tension reminds us that our cosmic blueprint is a living document, and now we have a powerful new tool for its revision. The James Webb Space Telescope is not merely an observatory, it is a time machine of unprecedented power, designed to read the earliest, faintest chapters of our cosmic story. While Hubble gave us a stunning view of the evolving universe, Webb peers back to its infancy, to an era when the first starlight was just beginning to pierce the primordial darkness. Its primary tool is infrared vision, allowing it to see through veils of cosmic dust that have long obscured our view and to catch the stretched, reddened light from the most distant galaxies as it journeys across an expanding universe. This capability transforms it into a cosmic archaeologist, digging through layers of time to uncover the very foundations of the cosmic web. Already, its initial observations have sent ripples through the world of cosmology. The earliest galaxies it has spotted are not the small, chaotic blobs many theories predicted. Instead, they appear remarkably massive and mature, with well-defined structures emerging far sooner than our models suggested. This presents a fascinating puzzle, forcing us to reconsider the timeline of galaxy assembly and the efficiency of those first bursts of star formation. By dissecting the light from these ancient island universes, Webb reveals their chemical fingerprints. It tells us the rate at which they were forging new stars and provides clues about the violent mergers that built them. Most importantly, it is giving us a direct, front-row seat to the epoch of reionization, that pivotal era when the first stars and black holes flooded the universe with ultraviolet radiation, burning away the leftover hydrogen fog and permanently clearing the cosmic stage. Each new image from this remarkable telescope is like finding a lost page from the universe's first diary, offering a clearer picture of how a simple, dark cosmos transformed into the complex, structured, and luminous reality we inhabit today. It is actively rewriting the origin story of cosmic architecture, one profound observation at a time. This static map of the cosmos is about to come alive. The Vera C, Rubin Observatory, perched high in the Chilean Andes, is preparing to open its eye to the sky and begin the most ambitious film project ever conceived. Its mission is the legacy survey of space and time, a 10-year epic that will not take a single snapshot of the universe, but a continuous, high-definition movie. Night after night for an entire decade, its massive camera will capture the entire visible southern sky, repeating the process week after week. This relentless observation will detect billions of galaxies, but more importantly, it will track how they subtly change and move over time. We will no longer see the universe as a frozen sculpture, but as a living, breathing entity. The true power of this survey lies in the sheer volume of change it will capture. It is expected to find millions of transient events, celestial objects that flare, flicker, or explode. Among the most critical of these are supernovae, the brilliant death throes of stars. Each one serves as a standard candle, a cosmic mile marker that allows us to measure vast distances across space. By compiling a vast catalog of these explosions from different eras, the survey will trace the expansion history of the universe with a precision never before possible, putting our models of dark energy to the ultimate test. Is dark energy truly constant, or does its strength vary over billions of years? The answer is hidden within this data, but the observatory's vision goes beyond tracking bright points of light. It will use weak gravitational lensing on an unprecedented scale. By meticulously measuring the tiny, systematic distortions in the shapes of billions of distant galaxies, astronomers will trace the invisible gravitational field of the dark matter that lies in front of them. This will allow us to create the most detailed three-dimensional map of the cosmic web's dark matter skeleton ever made, revealing the hidden architecture in stunning clarity. We will see how matter, both seen and unseen, flows along the filaments of the web and accumulates in the great clusters. This transformation from a static map to a dynamic movie of the sky will revolutionize our understanding of cosmic evolution, letting us watch the universe's grand design as it actively builds and changes. Flowing through you at this very moment are trillions of ghostly messengers from the dawn of time. Neutrinos, the second most abundant particle in the entire cosmos, outnumber atoms by over 1 billion to 1. For the first few seconds of the universe, they were trapped in the searing plasma. But they broke free incredibly early and have been streaming through everything, planets, stars, and even you, almost completely unnoticed ever since. Their ghostly nature comes from a profound lack of interaction, passing through solid lead as if it were empty space. Yet for all their elusiveness, these particles possess a tiny, crucial amount of mass. This minuscule mass transforms them from mere spectators into subtle influencers of the cosmic architecture. Because they travel at velocities incredibly close to the speed of light, they possess a unique kind of kinetic energy. When the gravitational pull of a small, nascent galaxy cluster tried to hold them, they simply streamed away, escaping the gravitational wells that successfully trapped dark matter and ordinary atoms. This cosmic slipstream effect had a specific consequence. It suppressed the growth of the very smallest clumps of matter in the early universe. The subtle gravitational tug from these fast-moving particles smoothed out the smallest ripples in the cosmic density field. We can actually measure this ghostly influence today. When we create incredibly detailed maps of the cosmic web, we find a slight deficit of small-scale galaxy clusters compared to what our models predict. It is as if the finest, most delicate threads of the cosmic spiderweb are fainter than they should be. This missing small-scale structure is the faint but measurable imprint of the neutrino, a fossil of their restless flight. By quantifying this suppression, cosmologists can perform a remarkable feat. They can weigh the ghost. The degree to which structure is suppressed tells us the sum of the masses of all three known types of neutrinos. This provides a critical window into fundamental physics that no particle accelerator on Earth can yet directly provide. These elusive particles, once thought to be massless curiosities, are now understood as essential contributors, their tiny weights subtly sculpting the grand design of everything we see. The grand cosmic web, with its sprawling filaments and vast voids, finds its ultimate origin not in the realm of stars or galaxies, but in the ghostly domain of the quantum. The very largest structures we can observe, from superclusters to great walls of galaxies, were born from the very smallest phenomena imaginable, microscopic quantum fluctuations. In the first fleeting moment of the inflationary epoch, the universe was a seething sea of quantum foam, a turbulent energy field where particles and forces flickered in and out of existence on scales trillions of times smaller than an atom. Within this chaotic foam, random jitters in the energy field itself created tiny, unpredictable variations in density. These were not physical ripples in space, but probabilistic hiccups in the very fabric of reality, the universe's inherent uncertainty written onto its youngest canvas. Then, in a breathtaking instant, the hyper-fast expansion of inflation took hold. It stretched these infinitesimal quantum irregularities, these mere statistical whispers, to astronomical proportions. A fluctuation that was once smaller than a proton was suddenly enlarged to span thousands of light years. This was the moment the cosmic blueprint was drawn. Those magnified quantum jitters became the subtle hills and valleys in the density of the primordial universe, the slight overdensities and underdensities that gravity would later seize upon. Without these random seeds, the universe would have remained perfectly smooth, a featureless sea of gas where nothing, no star or galaxy, could ever form. This is one of the most profound connections in all of science, a direct link between the bizarre rules that govern the subatomic world and the grand architecture of the cosmos. The entire cosmic web, in all its magnificent structure, is essentially a quantum fluctuation, frozen in time during that first explosive moment, and expanded to a scale beyond human comprehension. The pattern of galaxies we map across the sky is a colossal fossil, a magnified imprint of the universe's quantum mechanical origins. This realization provides a tantalizing hint of a deeper, unified theory of quantum gravity, a single framework that could describe both the force that builds galaxies and the strange rules that allow particles to be in two places at once. It suggests that the universe's greatest structures are, at their heart, quantum mechanical artifacts, written small at the dawn of time, and then stretched across the heavens for us to eventually discover. Our journey through the cosmic story is a humbling reminder of our own place within it. We have traced the path from a formless quantum blur to the sprawling cosmic web, a narrative that connects the very fabric of your being to the grandest structures in existence. The atoms that form your hands, the air you breathe, were all forged in the hearts of those first giant stars, scattered across space by their explosive deaths, and eventually gathered together on a small planet orbiting a stable star. This is not a separate story from the evolution of the universe. It is the most intimate chapter of it, The same fundamental forces that sculpted galaxies also govern the chemistry that allows life to flourish. With every new discovery, from the nature of dark matter to the accelerating expansion driven by dark energy, we are not just filling in a textbook, we are reading our own cosmic genealogy. The quest to understand this grand design is one of humanity's most profound adventures, a shared project that stretches across generations and cultures. It invites us all to look up at the night sky with a new sense of connection and wonder. What part of this cosmic story resonates most deeply with you? Share your thoughts and questions in the comments below. And if this voyage through space and time has expanded your horizons, consider subscribing for more journeys into the heart of the universe's greatest mysteries.